Okay, so continuing on our chapter 15 video lecture, the very end of the last video, I introduced this question. You're asked to find the pH of a 0.15 molar solution of ammonia. You need to recognize that ammonia is a weak base. To get the pH of a weak base, same steps as a weak acid. Number one, write your hydrolysis reaction and your Kb expression. Again, Kb, because now we're looking at a base. Previously it was Ka with the acid. Number two, ICE, filling in your initial values. Change minus x plus x, E, I plus C equals E. And step three, think, how do I solve for x? Okay, so with our ammonia, NH3, I chose to use the chemical formula NH3. You could just have correctly used the generic weak base B. So NH3 plus water to make ammonium anhydroxide. Our Kb expression, again, products over reactants, leaving out water because it's liquid. Icebox, 0.15 molar, because that was the molarity that was given in the problem. 0 for ammonium anhydroxide because nothing is mentioned, therefore we assume that they're 0. Minus x plus x plus x. Again, this is because the change, initially we have just NH3. Over time, the NH3 reacts, so the molarity will go down. You will produce with a 1-to-1 mole ratio ammonium and hydroxide. And then finally at equilibrium, you have 0.15 minus x, and x. Again, water, a liquid. It's not included in the Kb expression. We do not need to include it in the icebox. Put an X right there to remind myself. We leave that out. Now we're in step 3. Think, how do I solve for x? Well, we saw in the previous problem, the this should be Kb, was given. Again, Kb, because this is a base reaction, that's a Kb, so make sure you have your notes correct. Given as 1.8 times 10 to the negative 5th. Products over reactants. X times x is x squared over 0.15 minus x. We're going to go ahead and assume x is 0 so we can avoid the quadratic formula. Now we have our Kb equals x squared over 0.15. We can solve for x by multiplying both sides by 0.15 and taking the square root. And I got x equals 1.6 times 10 to the negative 3rd. We want to always go back and check, is x really small compared to the number I subtracted it from? X was being subtracted from the molarity of the ammonia, which is 0.15. So our x value over 0.15 times 100 is 0.64%. That tells us that x is really, really small compared to the number it's being subtracted from. So you could check. You could go ahead and redo this problem mathematically, solving for x with the quadratic formula, and you'll find that the x that you solve for with the quadratic formula is nearly identical to that, if not the same when rounded to 2 sig figs. So now we want to think, have I solved for x? No. Or I'm sorry, I solved for x, but have I answered the problem? No. The question was finding the pH. Well, now I look at my icebox. I see that x stands for hydroxide. So what can I solve with if I have the hydroxide molarity? I can get a POH equals, remember our equations you have to be really familiar with, equals negative log of hydroxide molarity. It's negative log of our x. I see that because x stands for my hydroxide molarity equilibrium. So the POH negative log of 1.6 times 10 to the negative 3rd. Put that into your calculator. Got POH of 2.80. 2 sig figs for the molarity. Gives me 2 digits past the decimal. Still haven't solved the problem yet. I need pH. Remember, pH plus POH equals 14 at 25 degrees Celsius. pH equals 14 minus our POH, and I got a pH of 11.2. So again, recap. We're asked to solve for the pH of a weak base, weak acid or weak base. Same steps, hydrolysis reaction and your K expression, icebox, and think, how do I solve for x? In this case, we are given a Kb, so we can solve for x. Once you get x, get a POH and a pH. Okay, so now we're going to look at the relationship between Ka and Kb. So I know that Ka for a weak acid tells you how far it will dissociate, Kb for a weak base, how far it will react. Well, if I have the Ka of an acid and the Kb of its conjugate base, I can multiply them together and get Kw. We'll derive this in class on Wednesday. For right now, just know how to use it. And what does this mean? This would be, for example, if I have the Ka of maybe NH4 plus ammonium, I would then have the Kb of NH3. So the key, you're always using this equation, Ka times Kb equals Kw, with a weak acid and its conjugate base, or a weak base and and its conjugate acid. Another example, if I had maybe the weak acid HF, the Kb I would be using would be F minus, the conjugate base of hydrofluoric acid. And we can see, I know that Kw is a constant, right, at 25 degrees Celsius, 1.0 times 10 to the negative fourth. So if this is a constant, as Ka gets larger, Kb gets smaller. So what does that tell me? As Ka gets larger, as your weak acid gets stronger, the Kb for the conjugate base gets smaller, or its conjugate base is weaker. So this goes back to a lecture from last week. The stronger the weak acid, the weaker its conjugate base. This is the mathematical kind of explanation of why that statement is true. Or the weaker the weak acid, the stronger its conjugate base. Other times you'll be using this equation. Sometimes you're solving for the pH of a weak base. You're not given the Kb for the base, but you're given the Ka, so you can solve it with this relationship. Okay, so let's look at this. Practice exercise 14. The base quinoline has the following structure. And again, I recognize, and I want you to start to recognize as well, what makes this a base: nitrogen with that lone pair. Remember, lone pairs can accept H+. And that is what a base does. It accepts H+. So its conjugate acid is listed in the handbooks as having a pKa of 4.90. What is the base dissociation constant for quinoline? Okay, so a couple things to think about. Remember, how do we relate between a pH and an H+? pH equals negative log of H+. So what does this P really stand for? The P in front of anything just means negative log of whatever that is. So how do I relate a pKa and a Ka? Well, a pKa is just going to be the negative log of the Ka. So with this information and the equation we had on the previous page, Ka times Kb equals Kw, you should be able to solve this problem. So go ahead, hit pause, solve this problem, put the numbers into your calculator, hit play again, and we'll go over it in a minute. Okay, so hopefully you were successful in working through this mathematically with your calculator. Remember, pH is negative log of H+, so how do we solve for H+ if we're given pH? H+ is 10 to the negative pH, and I'm writing this down because we're using the same rules for a pKa and a Ka. So here, we're given a pKa, so with this equation, I can solve for the Ka. So my Ka is 10 to the negative 4.90. Why do I want to do that? Because I'm trying to find the base dissociation constant. That is your Kb. Now we can use that equation, Ka times Kb equals Kw. It's a good idea to do the algebra first. Kb equals Kw over Ka. So that gives us Kb equals 1.0 times 10 to the negative 14th divided by 10 to the negative 4.9. You could have put this into your calculator already. I typically just save it for the end. So that gives me Kb equals 7.9 times 10 to the negative 10th. So again, we're given a pKa. We want to find the Kb for that conjugate base. First I solve for the Ka, then I solve for the Kb. Okay, so now we're going to go ahead and shift gears a little bit. So we're still in chapter 15. Now we're starting section 8, the acid-base properties of ions and salts. So up until this point, we've looked at the acidic properties of weak acids, the acidic properties of weak bases, strong acids, strong bases. Now we're going to look at salts. Remember, a salt is just a soluble ionic compound. So we're really just looking at our ions. So for example, if I have a generic anion X minus reacting with water. So remember, anytime you see a negative sign, think that could be a proton, or that could act as a proton acceptor to make HX and OH minus. So what do I have? What is this reaction? Like looking up, this would be a base. Water here is acting as an acid. Then HX would be the conjugate base, the conjugate acid. HX the conjugate acid, because I have the base accepting a proton to make the conjugate acid. The acid losing an H plus, right, an H plus donor to make the conjugate base. So here's an example of how an anion specifically, can act as a base. Another reaction is the reaction of cations with water. So, if I have a cation, this is just an example of any cation with a 1 plus charge, there's going to be a weak electrostatic interaction between water, so this would be oxygen, right, H2O, I know that water has a bent molecular shape, it's polar, there's a partial negative by this oxygen, so that means that any cation is going to be attracted to water, which is going to slightly pull the electron density toward the cation, making this H plus come off a little bit more easily. Now we could compare a 1 plus ion to a 3 plus ion, which is going to pull electron density towards itself more strongly. The 3 plus ion, making a 3 plus ion in water a slightly more acidic solution than a 1 plus ion. So here are two examples. An anion can act as a base by accepting a proton. And these cations will make water slightly acidic because it allows this H plus to come off more easily. So those are the two generic types of interactions we'll be looking at. And now we have 6 specific points. I've got 6 points here that are described in words. And then the very next slide, we're going to look at the chart from the study guide. So, effects of cations and anions, number 1. And these you do need to memorize, but if you can understand the reactions that are happening, it'll make it much easier to memorize. More like understanding versus just memorizing 6 points. So number 1, an anion that is the conjugate base of a strong acid will not affect the pH. So we did talk about this before. The anion that is the conjugate base of a strong acid will not affect the pH. For example, right, so what's an example of a strong acid would be HCl. So an anion that will not affect the pH would be Cl minus. Any of the conjugate bases of the strong acids will not affect the pH. That means the pH is going to equal 7. So we've talked about that one before. Number 2, an anion that is the conjugate base of a weak acid will increase the pH. What does that mean? Will increase the pH, that makes it slightly acidic. So an example, the anion that is the conjugate base of a weak acid. What's a common weak acid? HF. What is the anion that is the conjugate base of this weak acid? Is fluoride, F minus. And we'll increase the pH. Well, we understand that, right? HF is a weak acid. The conjugate base of a weak acid is a weak base. You could calculate a Kb here. Increase the pH, making it more basic. So that's really not too surprising. So we have 2 points here. They're both anions. If it's the conjugate base of a strong acid, the pH is going to remain the same at 7. If the anion is the conjugate base of a weak acid, it's going to increase the pH because that anion is indeed a base, a weak base. Point 3, a cation that is a conjugate acid of a weak base will decrease the pH That is, again, making the solution more acidic, or the pH will go down. Common weak base, NH3. What is the cation that is the conjugate acid of this? Well, this is our weak base. The conjugate acid, we add one more proton to it, so that would be ammonium. And I know that ammonium is indeed a weak acid. There's a Ka value I could calculate. Decrease the pH because it's slightly acidic. Again, weak acids have weak conjugate bases. The cation makes the pH go down. Weak acids have weak conjugate bases, so that anion makes the pH go up. An anion that is a conjugate base of a strong acid will not affect the pH. Point 4. Cations of strong Arrhenius bases will not affect the pH. So what are these? These are the strong bases: sodium hydroxide, potassium hydroxide, calcium hydroxide, etc. All of those cations will not affect the pH. What does it mean to not affect the pH? It's going to equal 7. So I remember the anion of a strong acid doesn't affect the pH of 7. Cation of a strong base doesn't affect the pH of 7. 5. Other metal ions will cause a decrease in pH. And let's think about this. What is a metal ion? What do metals do? Do they add electrons or do they lose electrons? Remember, metals lose electrons to form cations. So these cations decrease the pH for the reason that we saw on the previous slide here, shifting the electron density of oxygen towards itself, making water slightly more acidic. So decrease the pH, making water more acidic. The last one, when a solution contains both the conjugate base of a weak acid and the conjugate acid of a weak base, the effect on the pH depends on the Ka and the Kb. So what is this saying? Your cation is a weak acid, calculate the Ka. The anion is a weak base, calculate the Kb. Whichever one is larger tells you if the solution is acidic or basic. So if Ka was larger, the solution would be acidic. If Kb is larger, the solution will be basic. And this will have an example in our pre-lab calculations for our pH experiment. Okay, those same 6 points I put together in a different chart, so you have 2 different ways of looking at it, and this is in your study guide. So I categorized it based on if it's either an anion or a cation and how it's going to change the pH. So again, the points we're going to go over right here are the exact same points from the previous slide, just in a different format. So anions, you've got 2 choices. Conjugate base of a strong acid, remember no change to pH, that means my pH will be 7. Conjugate base of a weak acid, if the anion, it will increase the pH. Why? Because the anion, that's the conjugate base of a weak acid, is a weak base. So our pH is going to be greater than 7, which is basic. Cations, 3 options. The cations of the strong Arrhenius bases, so the cations of the soluble metal hydroxides, no change the pH, so it's going to be 7. If the cation is a conjugate acid of a weak base, that was the ammonium example we saw from the previous slide, it's going to decrease the pH because the cations that are the conjugate acids of the weak base are indeed acidic, so the pH is going to be less than 7. And lastly, all other metal cations also decrease the pH, giving us a pH less than 7. So, if you think about it, if it's the cation or the anion related to a strong acid or a base, pH is 7. All other anions, the pH is greater than 7. All other cations, the pH is less than 7. So hopefully that will help you remember it as well. Okay, so let's see. How are we going to apply this concept? Multiple choice questions are very common for exams with this question, with this concept. Practice exercise 15 is an example of that. States in each of the following, indicate which salt in each of the following pairs will form the more acidic or less basic 0.010 molar solution. So the molarity is given so you know that the molarity is all the same. So more acidic, less basic, that just means I want the more acidic, less basic That's our lowest pH. So I will start you with A, and then I'll have you pause, look at B, C, and D on their own. So a couple things to think about. These are all salts. They're ionic compounds. For all of the ionic compounds we look at for this type of a problem, we'll have one cation and one anion. So you want to think about them separately. Sodium is a +1 ion, and this is the cation of a soluble metal hydroxide, so its pH is 7. Does not affect the pH, so have that chart from the previous slide out. It is in your study guide. Nitrate, NO3-. This is the conjugate base of a strong acid, so this pH is also 7. So overall, sodium nitrate, pH of 7. Now we have nitrate again. This pH is 7. Iron 3+. Well, this isn't the cation of a soluble metal hydroxide. And remember that all other cations have a pH that is less than 7. So overall, less than 7 and 7, our pH will be less than 7. So then which one will be more acidic or less basic? That will indeed be iron 3 nitrate. Okay, so go ahead, hit pause. I want you to think about all of these others, just like we did before, and we'll go over them together. Okay, so hopefully you had a chance to think about these. I'm going to start by writing out the cation and the anion. So K+, Br-. Over here, KBRO. This might be a little bit confusing if you haven't thought about these polyatomic anions in a while. So what I want you to recognize is the fact that you know that potassium is K+. That means that BRO is a polyatomic anion, BRO-. Okay, so let's think about this one. K+, this is the cation of a soluble metal hydroxide, so its pH is 7. Get it over here. Br-, conjugate base of a strong acid, so its pH is 7. So overall, KBr will also be 7. KBRO, again, well, potassium is 7. BRO- is not the conjugate base of a strong acid. Therefore, it's the conjugate base of a weak acid. So its pH is going to be greater than 7 because it's basic. So which will have a lower pH? 7, or overall greater than 7. KBr, lower pH. Okay, over here, I have a salt. I know it's a salt because we're told it's a salt. I recognize immediately my anion Cl-, which is the conjugate base of a strong acid, so its pH is 7. That means that this entire other group of atoms is a polyatomic cation, CH3, NH3. And because Cl is -1, this must be +1. It's a cation. It's not the conjugate acid, or it's not the cation of a soluble metal hydroxide, so it must be a cation that is the conjugate acid of a weak base, which it is. So it's a weak acid, so its pH is going to be acidic, or less than 7. So I have less than 7 and 7, and over here, barium, which I recognize as the cation of a soluble metal hydroxide. So that gives me a pH of 7. Chloride, conjugate base of a strong acid. Its pH is also 7. So overall, I've got barium chloride with a pH of 7. CH3NH3Cl, which has a pH of greater than 7. So which one has a lower pH? Well, that would indeed... I'm sorry. So I have 7, or a pH less than 7. There we go. Lower pH, more acidic. Okay, last example. Ammonium nitrate, NH4+, I know is the conjugate acid of a weak base. Therefore, it has a pH that is less than 7. It's acidic. Nitrite, NO2-, conjugate base of a weak acid. So it's basic. Its pH is greater than 7. Over here, ammonium nitrate. I know ammonium is, again, conjugate acid of a weak base. It's acidic. Its pH is less than 7. And lastly, nitrate, NO3-, conjugate base of a strong acid, so its pH is equal to 7. So which pH is going to be lower? Ammonium nitrite, where the cation is less than 7, the anion is greater than 7, or ammonium nitrate, where I have a pH less than 7 and this equal to 7. The lower pH, yeah, you're right, will indeed be ammonium nitrate. And you have some additional problems like this on practice exams and mastering chemistry. Recap of the answers. There you go. If you need to get them down again, feel free to pause. Okay. Oops. So here, practice exercise 16. If a 0.15 molar NaA solution has a pOH of 5.45, what is the Ka of HA? Okay, things to think about. NaA, this is a salt. It's a generic salt. We know that Na plus is a cation, A minus is an anion. We know how to think about the acidic and basic properties of a salt. I know that sodium does not affect the pH. Its pH is equal to 7, so we can ignore it. A minus is the conjugate base of a weak acid. I know that because I'm asked to get the Ka of HA, therefore A minus is a weak base. How do we get the pH of a weak base? Hydrolysis, Kb expression, icebox, and think. So go ahead, write down your hydrolysis reaction, get that icebox, think, how do I solve for X? You'll be using this information to solve for X, to solve for your Kb, and lastly your Ka. So go ahead and pause it, work through that. We'll go over it together in a minute. Okay, so we're going to go over this together. Here's that information that was given. You're given the molarity of a salt. I know that sodium doesn't affect the pH, so we can ignore it. I'm going to focus on the reaction of A minus with water. Right, number 1, hydrolysis reaction, Kb expression. Number 2, ICE. Number 3, think, how do I solve for X? So we've got our hydrolysis reaction. Weak base with water to make conjugate acid in our hydroxide. Kb expression, ICE. Then I have to think, how do I solve for X? Well, X is my hydroxide molarity, and we're given a pOH. Well, I know I can solve my hydroxide by taking 10 to the negative pOH. So that's 10 to the negative 5.45. I know X, so I can solve for Kb, right? X squared over 0.15 minus X. So I plug in 10 to the negative 5.45 for X. I have 8.39 times 10 to the negative 11th. I underline that 3 because I'm looking at 2 sig figs. Once I get Kb, I can get Ka using my Kw reaction, or equation, excuse me. And there we go. So again, a salt, all you have to do is look at the cation, look at the anion, figure out which one will affect the pH, and go from there.